Okay, so our next talker is Matthias. Matthias is at Western Sydney University doing a PhD, I believe, with Associate Professor James East. So take it away.
Thank you, Kane. So today I'm going to talk to you about the Congruence Lattices of Finite Twisted Brauer and Temperley-Lieb monoids. So as the title suggests, there's going to be two main ingredients for this talk. First, monoids, and then second, congruences. For both of these, I'm going to go through some definitions and examples, and then tie that back to the results I was able to prove in the last couple of years. To begin with, let's start off with some motivation, and this comes from the field of statistical thermodynamics. And in this particular field, the atomic interactions between atoms is modeled by matrices. Specifically, these matrices are elements of an algebra, usually a twisted semigroup algebra. And that semigroup here is actually the Brauer monoid. This whole construction is then usually called the Brauer algebra. So we can see if we have a better understanding of the Brauer monoid, in this case, we get a better understanding of statistical thermodynamics. This is not the only use case or example. Other fields that make use of these monoids include biology, representation theory, invariant theory, as well as knot theory. So what exactly is a monoid? Well, it's a set together with a binary operation, and this binary operation is associative. So if I multiply three things together, the order doesn't matter. And likewise, we have an identity element. So essentially, I can multiply it by the identity, and I'm not really doing anything. We're going to be interested in not just any monoid, but two specific ones. First is the zero-twisted Brauer monoid, and it has as its elements the Brauer diagrams. Pictorially, we can represent these as two rows of vertices numbered from left to right. And what makes diagrams different from each other is the edges. So Brauer diagrams have the condition that every vertex must be connected to exactly one other vertex. So we're sort of pairing up vertices, if you like. The other monoid we're going to be interested in is the zero-twisted Temperley-Lieb monoid. And this is sometimes referred to as the Jones monoid. And if you were keen-eyed, yes, this is the same Jones as the author of the motivating example paper. It holds the Temperley-Lieb monoid is actually a submonoid of the Brauer monoid. So most of the time when I'm talking about Brauer, I sort of implicitly also can be talking about Temperley-Lieb. Considering as it is a submonoid, its diagrams has an extra condition, and that extra condition is that edges are not allowed to cross like they do up here. The graph must be planar, but we also need to be planar within the box of the vertices. So we're not allowed to have edges going around, for example. We can talk about the degree of an entire monoid, and this simply counts the number of vertices we have in our row. So both of these belong to a monoid of degree 5. We can talk about the rank of a specific diagram, and this counts the number of transversal edges. So transversal, meaning linking the top and the bottom rows. So here we have 1, 2, 3. This diagram has got rank 3. Here we have a rank 1 diagram. It holds that the rank and the degree always share the same parity. And finally, we have an abstract 0, which we call a diagram, even though it doesn't actually have a visual representation. And this just behaves like a 0 as you would expect. And just to note, this 0 has got nothing to do with this 0. Just don't get confused there. That 0 has got some other meaning, which I'm not actually going to explain, but not because of the 0 diagram. For our monoid, we need a multiplication operation, and that is the concatenation operation. For those of you that are visual-based learners, this is an animation of that procedure in action. And for everybody else, we're going to use these intermediate steps to show how do we end up at the concatenated diagram. So let's go through the steps for calculating alpha times beta in detail. First, we position the two diagrams, one directly on top of the other, and then we draw these red vertical in-between edges. We then remove the two inner rows of vertices, and then we remove any loops. So a loop is a collection of edges that are not connected to the top or the bottom row of vertices. So we have an example here, and we have a second example here. And then we just tidy up what we have left. So we're just going to squish our rows back to normal size and draw clean edges where we have edges being present. except I lied. We don't actually remove the loops. That is the non-twisted concatenation. In the zero twisted concatenation, as soon as we encounter a loop, as we do in this example, then just by definition, we have the zero diagram. Visually, we can see that this operation is going to be associative, and it does have an identity, specifically just all vertical edges for the diagram, but it's not necessarily going to be commutative. For those of you that are familiar with it, this does correspond to a Brauer, respectively Temperley-Lieb algebra with a twisting coefficient equaling to 0. Now let's move on to the congruences. What exactly are they? Well, they're an equivalence relation, usually denoted sigma, on our set of diagrams, but it has to be compatible with concatenation. And by that, we mean if I take a diagram alpha that is congruent to some beta, if I multiply on the right by any other diagram, say gamma, that pair must also be congruent. And I want the same condition to hold for on the left. Some easy examples include the universal congruence, where everything is congruent to everything else. And similarly, the trivial congruence, where everything is only congruent to itself. So in between these two extremes, we're going to have a lattice, the congruence lattice. So we can picture this as having the trivial congruence at the bottom, universal congruence at the top, and all sorts of different congruences sitting in between these two. And we can think of this lattices in one of two ways. One as a partially ordered set with subset inclusion. So for example, sigma 10 here would be a strict subset of sigma 11. Or we can think of it with two operations, the join operation and the intersect operation. So join makes a congruence bigger, so we can join, say, sigma 4 and sigma 5 to give us the bigger congruence sigma 6. Or alternatively, we can take their intersection, which makes the congruence smaller, and in that case, we would get sigma 3. If I were to take an arbitrary monoid and look at its congruence lattice, it would be horrendously complicated and large and not really of any practical use. It's very remarkable fact that for the partition diagrams and the diagram monoids in particular, that our congruence lattices are very simple and can be as simple as just a chain. We will need the notion of a principal congruence. This is where we take a pair alpha and beta and we look at what's the smallest congruence that contains that pair. Why do we care about congruences to begin with? Well, because they govern quotients in exactly the same way that ideals are important for rings or normal subgroups are important for groups. And if we go back to a motivating example where we have the Brauer monoid appear, well, usually it's not actually the entire monoid that appears, it's usually a quotient of it. So for us, being able to understand the congruences allows us to understand the quotients that we need in that example use case. Before I continue, we need to take a quick dive into some semigroup theory tools, specifically Green's relations. So these are also equivalence relations on our set of diagrams. We have the R relation, and two diagrams are related if their top row is the same. And by that we mean if their vertex is part of a transversal edge, in the other diagram it is also part of a transversal edge. And similarly for non-transversals. But for the non-transversals, it's really important to note that the actual edge must be the same across both diagrams, otherwise they're not R related. In an analogous way, we have the L relation, and this is where the bottom row of our two diagrams has to be the same. We can take the intersection of these two. Logically, that means both the top and the bottom rows have to be the same. And it holds that our H classes are in bijection with the symmetric group of that rank. And we can see that in the example here, we have rank 2, and we have the two elements of the symmetric 2 group appearing. This bijection is going to be important, so keep it in mind for later on. And also keep in mind that in the Temperley-Lieb setting, the H relation is trivial. And we can see that quite easily if you think of the symmetric group. Remove all the elements that do have any crossings. All you're going to be left with is the identity element, just one element, that's the trivial relation. Instead of intersecting, we can take the join of R and L, that gives us the D relation. And the D classes are all the diagrams with a given rank. The ideals are all the diagrams with a given rank or less. And the final ingredient we're going to need is a hat map. This is defined for even degree. And essentially, it just takes a pair of transversal edges and it annihilates them in the obvious way that you would expect. So that now allows me to state the congruences we are going to need. And I'm going to explain these using an egg box diagram. And this is going to be for the monoid of degree 6. So we can picture an egg box diagram as being full of little dots, where each little dot represents a diagram in our monoid. So at the bottom, we would have the 0 diagram. Then in here, we would have all of the diagrams of rank 0, so the D0 class, all the diagrams of rank 2, 4, and at the top, rank 6, which is actually the whole entire symmetric 6 group. If we have 2 dots, so 2 diagrams in the same row, then we know they are related. And analogously, if they're in the same column, we know they are L related. Hence, if they're actually within the same box, then we know they are H related. So if we were to zoom in on, say, this top corner here, we're in D2, so we have diagrams of rank 2. All of these have 2 transversals. Within one of these boxes, we're H related. So both the top and the bottom rows match up between these 2 diagrams. If we move within a row, we are R related. So our top rows have to be the same. Yep, all these 4 diagrams have got the same top row. And if we move down in a column, we're L related. So our bottom rows have to be the same. Yep, that's the case as well. So the first congruence we're going to go through is the Riesz congruence. And this is where we just collapse the P ideal to a single representative. So as an example, let's look at Riesz 2. Everything of rank 2 or less, so that's everything in red here. We're just going to collapse that and think of it as one representative. For all of these congruences, I'm going to have an example pair of diagrams that are related by that congruence. And that pair is always going to be the largest possible pair under that congruence. Next, we have some group-based congruences. And this is where we take the rank underneath. And in the rank, we're looking at if we are H-related. Recall that gives us a bijection into the symmetric group. If I then have some group action, which I'm not going to define, then we're also congruent. So looking at an example of, say, the alternating 4 group, we have R2, so everything in the second ideal being collapsed. And then within a H class in rank 4, well, the alternating group has got odd and even elements. So we're going to get 2 equivalence classes. You can see that here. And this gets repeated across each of the H classes in D4. But it is important to note that the actual equivalence classes are different across the H classes. A different example would be the symmetric 4 group, where we again collapse the second ideal. But this time, the symmetric 4 group action is much more encompassing. In fact, anything that's H-related is going to satisfy symmetric 4 group action. So we're going to collapse our H classes in D4 in their entirety. Next, we have some lambda-based congruences, starting with lambda up, where we take RS2 as a starting point. And in rank 2, we have the extra possibility if we are R-related and have the same hat, then we're also. So recall RS2, collapsing our 0th ideal and collapsing H classes in D2. Now, if we're R-related, so within the same row, if our hats are the same, we're also congruent. So potentially some of these H classes can get identified across a row. And this gets repeated across each row. And again, with different equivalence classes. In an analogous way, we have lambda down, and this is where we swap out the R relation for the L relation. So that means potentially our H classes are now identified across a column compared to a row previously. And then we just have plain lambda, and this is where we drop the R or L condition altogether, and it holds this is the join of lambda up and lambda down. So here, our H classes potentially get identified across a row or column as long as the hat is the same. And the final congruences we're going to go through are the mu congruences, starting with mu S2, where in rank 2, we're just going to collapse our H classes, so very simple congruence. And then mu cline 4, our most complicated congruence, where we take lambda as a starting point. And in rank 4, if we're H related, we have the cline 4 action. So recall lambda, everything in the 0th ideal being collapsed, H classes in D2 being collapsed and identified across a row column as long as their hat is the same. And then in rank 4, within a H class, we have the cline 4 action. That gives us 4 equivalence classes. I've only drawn 2 here because I'm starting to run out of colors. And again, this gets repeated across each of the H classes with different equivalence classes. So that allows me to state the results I was able to prove, starting off with the Brauer result. So here, all of the congruences that I just went through with you are in fact all of the congruences for this monoid. And the congruence lattice is in the odd degree, a simple chain where we find the Riesz congruences, interleaved with the group-based congruences, as you would expect if you're familiar with this field. And in the even degree, we have this same chain, but we do have 3 diamonds at the bottom. And this is where we find the lambda congruences and the 2 mu congruences. From this, it's not too much more work to show that the Brauer monoid is congruence permutable. In terms of a proof of this result, well, the first step is to prove that all the congruences that I claim are congruences are in fact congruences. And then I need to consider every possible pair of alpha and beta and look at what's the principal congruence that pair generates. I need to show that congruence is contained in my list of congruences and that the list is closed under joins. Once I have done that, I can apply a helpful lemma by East, Ruškuc, and Temperley-Lieb, which says that my list is in fact the entire list of congruences for the monoid in question. So to give you a bit of a better sense of checking all of the different alpha and beta combinations, this is the decision tree that I went through. And in red for each leaf is going to be the corresponding congruence. So first up, I check, do we have different diagrams? Is one the 0 diagram? Do they have different ranks? Are they H related? I look at some low ranks, mostly to pick up on the diamonds on the even setting. And then over here, if they have the same hat, I then need to look at exactly why are they not H related to work out which flavor of the lambda congruence we get. And over here, we need to take care of the Klein for action. The Temperley-Lieb result, well, it turns out that its lattice is actually a sublattice of the Brauer lattice. So recall the Brauer result and further recall that the H relation is trivial on Temperley-Lieb. So group-based congruences, they contain the H relation, they're going to disappear. And likewise, the mu congruences, they're going to disappear as well. So what are we left with? Well, we're left with the Riesz and lambda congruences. They're all that is possible in Temperley-Lieb. And the lattice in the odd degree is still a chain, but this time with just Riesz congruences. And in the even degree, we almost have a chain with one diamond where we find the lambda congruences. Not surprisingly, Temperley-Lieb is also congruence permutable. So this research program was started back in 2018 by East, Ruškuc, and Temperley-Lieb, who investigated quite a sizable collection of diagram monoids in the non-twisted setting and found their congruence lattices. This was then followed up by East and Ruškuc in 2022, where they looked at the partition monoid, but in a twisted setting and found its congruence lattice. So for me, the next step sort of as part of this larger research program would be to go from the 0 twisted setting of Brauer and Temperley-Lieb to an arbitrary D-twisted setting. And then one step beyond that would be to move into an infinite twisted setting, where sort of in hand wavy terms, D is equal to infinity. Throughout this work, I've also developed a LaTeX package called PM Draw that's available on CTAN for you to use and explore if you need to draw these diagrams. So all of the diagrams you've seen in my talk have been drawn using this package. And this is an example of one of the diagrams that I've drawn for the actual formal proof. And just a crazy example here to show you what it is capable of doing. And if you do want some more details, there is a full-length lecture version of this talk on my YouTube channel. You have a QR code here, or you can check out the URL there. Hopefully you have learned some interesting maths with the help of diagrams.
Thank you, Matthias. And yeah, very, very nice diagrams. So I'm wondering if I can use this package for any of the diagrams I draw in my maths.
Please do. I'm happy to assist as well if you need some help or if there's missing features that should be added. It's not complete yet, like it works, but there's definitely improvements that can be made.
Okay, cool. Does anybody have any questions for Matthias? I guess I have a question about this arbitrary decay. So by this you mean that there's going to be so when you have these sort of loops, then you have to count them in some way. I'm not
Yeah,
100%
so
sure.
if we go back to the very start, oops, that's a bit too far. So the zero in the zero twisted basically means here that we're allowed to have zero loops in our concatenation process, which obviously means like we're not allowed to have any. If I say like pick d is equal to 2, I'm allowed to have up to 0, 1, or 2 loops in a diagram, and we sort of keep track of how many loops have we got.
Okay.
And then obviously in the infinite setting, it's I don't care how many loops I have, like in the sense there's no limit, but I still need to keep track of how many loops have I got.
Okay, cool. Do you think somehow that the infinite case might be easier than just choosing some finite d?
No, it is much more complicated. And in fact, the work that was done on the partition monoid, the actual write-up of it is basically all in the infinite case, and then sort of you can pull out like a finite d or even d equaling to 0, sort of as a special case, and just think of it as a quotient. So sort of the key result is to get the infinite case, really.
Okay. Cool.
Hey, Matthias. Jerry here. Does the size of the loops matter at all?
No.
Okay.
It's just the fact that there is a loop.
Okay, cool. Thanks. Nice diagrams.
Thank you.
Okay, if there's no more questions, then thank Matthias again.